Let's go ahead and jump into instrumental variables, and like every other day, let's just, when you have questions, just put it in chat and we'll stop and we'll answer them, and we can, don't worry if we've passed something, we can go back. It's not a big deal. Okay, so let me go ahead and start this. So we were talking about that Angrist and Kruger paper, and I had said that one of the things they did was they wanted to increase the precision of their estimates. So they added more instruments. I think it was either Melba or Angelica that was asking about, adding in more instruments. And usually the problem with adding in more instruments is it's inevitable that you end up with some weak ones. What does that mean? That means their partial effect, independent of the other instruments, ends up being weak, not very highly correlated, not very precise, ends up being something to do with the sample not being as large as needed. So this did cause their standard errors to get smaller. So you can see right there, they decrease, gets their larger coefficient, and their standard errors decrease. Then they do some more specifications of it. But this issue of 180 instruments and some of them being weak gets the attention of some applied econometrician types. So let's consider a model. All right, let's consider this model. And what we're going to do is we're just going to highlight the issue that they may be facing mathematically. We're just going to go through and try to understand this issue that I've kind of been alluding to a little bit better. So this right here is the model. This is the structural model. You've got some outcome and you've got some variable, and this is a causal variable. And we're just kind of, for simplicity, assuming that everything's subsumed to V. And one of the things you'll hear is you'll hear this language here: one instrument, one endogenous variable. Okay, this is called a just identified model. If you have one instrument and one endogenous variable. All right, if you have more than one instrument, one endogenous, more than one instrument, one endogenous variable. Okay, so something like that. This is called over-identified. Over-identification can be an issue if some of those instruments are weak. All right, it can be an issue if some of those instruments are weak. So I got to stick with some matrix notation here. But I teach real slow, as you guys have seen so far. So this shouldn't be that bad. All right. So the matrix of IV, this is a first stage equation right here. So this is a first stage. All right, is we've got X as a function of Z. Okay, so this is pi again, and with pi, what was it before? Beta. All right, so I don't have the reduced form. So this is the first stage equation. And here's the Z term. And this right here is called the residual maker. That's what we used to call it in graduate school. We used to call this matrix right here the residual maker. It makes residuals. And it's got this expression right here, Z prime, Z inverse, Z prime. We're going to use it a few times. It's very common in a panel econometrics class taught with matrix algebra to see that residual maker used over and over and over again. So you've got V here, the structural error term. V is the structural error term. in the causal model. Okay. All right. And then eta is the first stage error term. All right. Eta is the first stage error term. Okay. Let's put that right there. So if eta here, structural error term, and eta, if V and eta are correlated, okay, what does that mean? That means that OLS will be biased, all right, because look what it's going to mean. I've got this unobserved determinants of eta here and this. So now X has an error term and it's correlated with this error term. All right. So if they're correlated, you estimate the first equation by OLS, it'll be biased. And here's the OLS bias. So we've got this coefficient here. We've got this random variable here, beta. Sorry, we've got this constant here. This is the true causal effect, and this is a random variable. All right, so you run this 50 times, you get different values of OLS. All right, the difference between the two on average is a regression coefficient. Look how it's a scaled covariance, right? And so the regression is basically V onto X. Okay, and so B ends up being covariance XV variance X. All right, there it is right there. All right, so the difference between these two ends up just being the correlation between the structural error term and X, the degree of endogeneity. This is going to measure the endogeneity here. The degree of correlation scaled by some variance term. All right, and we're going to call the bias, this right here, we're going to call this bias this. It's going to be the same thing. All right, it's going to be the same thing. And if they're correlated, the bias is going to just be eta. It's going to be V eta because eta is the first stage error term. So this is X. I'm just going to write some of this down. X equals pa Z plus eta. All right, so we get this eta term. And then we also have Y equal BX plus V. Let me just get all this stuff in one place so I can summarize what's on this here. So this is if you run this regression, you're gonna get a beta OLS. The difference between beta OLS and true beta is covariance between V and X. Right. So there's the error, there's the correlations, the degree to which X and V are correlated, scaled by the variance of X. All right. And if so if V and eta are correlated, then it becomes just the covariance between this term and this term, scaled by this term. All right, so this is just a rewriting. We have rewritten the bias of OLS as sigma V eta sigma squared eta. Okay, that's the bias of OLS. That's the bias of OLS. All right, we're going to come back to this in a second. What we're going to do now is we will see how does weak instruments in IV relate to the OLS bias. How's it going to relate to it? That's one thing we're going to see. And what causes that bias to decrease? All right. Those are the two things we're going to try to answer. All right. So we're going to, now what we're going to do is we're going to derive the bias. We're going to derive the bias of two-stage least squares. So this we did a minute ago, the bias of OLS, that was that sigma eta V sigma squared eta, right? So that was the bias of OLS. Now we're doing the bias of two-stage least squares. We're going to see if it has anything to do with that. Okay, and it will. So here's the beta hat two-stage least squares. So you estimate two-stage least squares, you get a coefficient beta hat. And what you did was you used this as your first stage. Use that instrument, get an X hat, insert X hat into X, you run that regression and you get beta hat, okay? And that's beta hat right there. Now its matrix expression is this right here. It's producing fitted values this way. This is a different representation of it, but it's essentially the same thing with the set of steps that we talked about yesterday. Now, PZ, remember, PZ equals Z, Z prime Z, inverse Z prime, okay? Z prime. So we're going to put Z prime, Z prime, inverse Z prime into here, okay? And we're also going to put in the definition of Y. Actually, I think that's all we do. Let me back up. I took off some steps here. We're going to put the definition of Y into here, right? So let me do that again. We're going to put that into there. So let's rewrite that. I would draw it, but I don't have my stylus. X prime PZ X inverse X prime PZ BX plus V. Okay. And then we get X prime PZ X inverse X prime PZBX plus X prime PZX inverse X prime PZV. Okay, so all we did was we distributed this. First I did this one, that's here. Then I did this one, and that's here. Okay, now this beta term moves to the front. Now look real closely at this. X prime PZX inverse, X prime PZX, that will cancel out. Let's double check something. That'll cancel out. So you end up with this going away. Okay, because that cancels out. We get this. Here we have beta, X prime PZX, X prime PZX, inverse, X prime PZV. Okay, so all we did was we took the structural causal model, just plugged it into here, and just rewrote the definition of two-stage least squares. So all this was rewriting our solution to beta two-stage least squares by substituting the causal model into the expression. All right, that's all that we did. Right. Okay, now Now let's focus on the bias of two-stage least squares. The bias is shown by comparing our two-stage least squares solution to the true value of beta, right? If they are this, but remember, we will need to take expectations, because two-stage least squares beta is actually a random variable due to the frequentist tradition of considering the estimator as one value among all hypothesized sampling. All right, so we're gonna have to take the expectation over all of the. So it's basically like right now what we have is this, and this right here is beta two-stage least squares. We have, yeah, so we may have this, we could have this beta, right? It's going to have a mean of this, but we may have this one right here. So it's got this variance. It's got this variance here. And right now we're just going to do this minus beta. But in a minute, we're going to take the expectation, and that's going to be the expectation over all of the beta two-stage least squares. Okay. All right, so let's look through this. So we go beta hat, that's here. All right, so this is beta hat. All right, so what we've done is, I'm going to delete this. Start with our definition, and we're going to go this minus B. Okay, because that's what that is right there. All right, that's what that is right there. Well, if we do that, that cancels out. That cancels out, right? Because the betas are on both of them. So they delete, and we end up with this term. All right. And I'm just going to change some of these words around. So I'm going to say, instead of this here, I'm just going to call it A. Okay, so I'll call that A. I got that right there. And now I'm going to put in the definition, and X equals Z pi plus, was it eta? Okay, so this is going to become A Z pi plus eta PZV, I think that's right. Let's see if that's what we get here. Is that the same thing? A Z prime pi eta PZV. Yeah. All right. And then what we're going to do is we're going to distribute this term. Okay. So then we're going to distribute it. We're going to get A Z prime pi prime V PZV plus A eta PZV. Now we're missing some stuff. So let me just see if I have a typo. I have right here Z prime PZ. Let's do that here so we know. Remember, PZ equals Z prime Z inverse Z prime. All right. So if I'm going to multiply Z prime PZ, I'm going to get Z prime Z inverse Z prime. That's going to cancel out. I'm going to get Z prime, which is what I have here. Okay. Let's go through this again. So I get A Z prime pi prime V plus, because that's all I got right there. I did have Z prime PZ right here. The pi would have just come out. I'll just make that more explicit. All right. So that right here just equals Z prime. Okay. Plus A eta prime PZ B. Okay. So I got that A prime, A pi prime. Now I'm just going to plug the true value of A back in. Okay. Plug that back in. So we're going to get X prime X inverse Z prime pi prime V plus X prime X inverse eta prime PZV. See if I get the right thing here. Oh, yeah. Forgot. It's got a PZ in here. I know it's got a PZ. You can see right there, PZ. So what I did was I just remember that had been that. So I just plugged it back in. Okay. And so then I get the same thing. So everything else should be the same. Okay. All right. So this is the bias of two-stage least square, or this is the starting point of the bias of two-stage least squares. We're going to have to take expectations of this entire equation. But the bias of two-stage least squares is going to come from the non-zero expectation of terms on the right-hand side. Even though Z and V, right? So we have a valid instrument. We have a valid instrument. Z is independent of the causal error model, causal error V, all right? Okay, but we're going to struggle. We're going to struggle here for this to go to 0. We're going to struggle for one of these terms to go to 0. Right. I think I can get rid of this one. So I'm going to get rid of that. I'm going to get rid of that. See what I don't need anymore. Oh yeah, I don't need any of it. All right. So Angers and Pischke. Note that it's hard to take expectations of that equation because the expectation operator won't pass through that. You know, it won't pass through this, so you can't take expectation. So what we're going to do is, but we can take the expectation of the ratios in the second term. They can be closely approximated. So I'm going to take this. This was the equation that we just had. We're going to take expectations of it. We're going to get expectation for this one. Won't pass through it. So it's just going to be the whole thing. And then we take the expectations of this one right here. Then we take the expectations of the whole term here. And then we take the expectations of this here. All right. Let's see. Let's write this down so we can carry it to the next page. Expectation. Beta two-stage least squared minus beta equals expectation. So this will be X. It's too much. It'll take too long. So we'll just go back and forth. We'll go back and forth in a moment. All right. Now let's think about what we know. We know this is 0. This is 0 because remember, V is the causal error. Eta is the first stage error. All right. So Z and V are independent. All right. By exclusion. So that means this is implied by exclusion. This here, let's look at this one. So this is Z and eta. Z and eta. This is just saying what is this saying? So this is saying that Z is independent. Z is independent. Z is not endogenous in the X in the first stage equation. That makes it where Z and eta are independent. Okay. So we've properly specified the first stage. Properly specified the first stage. This is guaranteed to be, so this is a first stage. This is a first stage expression, right? We know that we get zeros from both of those. So we're going to let this expectation eta prime PZV. Let's go back and see what that was. PZV here. So we got this right here equaling 0. We're worried about this one. All right. We're worried about, let's look at this one. So when we let B, so we took those expectations through, and when we took those expectations through, this disappears. All right, because that right there is 0. All right, that's why this is shorter. That's why it's shorter. Okay, so we're left just with this term. We're going to call that B. All right, we're going to call that B here. All right, so a lot of the work we're going to do right now is going to be plugging in. We're going to be plugging in. We actually, I don't know why I put this here. We're going to skip this for now. We're going to go from this line to this line. Okay, so what I'm going to do is I'm going to plug in values of X. Okay, so remember, X equals pi Z plus eta. All right, so what we're going to do now is we're going to plug that in. Okay, that's going to give us expectation pi Z plus eta prime PZ pi Z plus eta. Okay. Right. Inverse B. All right. So when I did that right there, this became this. And this is irrelevant. And so then we get this expression right here. So this is the same thing. It's the same thing. Okay. And now what we're going to do is we're going to open up this PZ term here. We're going to distribute this PZ term. And what it's going to do what it's going to do is it's going to distribute this PZ in here. So let's write down PZ again. PZ equals Z, Z prime Z, inverse Z prime. All right. So now we're going to get expectation pi Z prime, because we got this prime here, Z prime Z, Z prime Z, inverse Z prime eta prime. Okay, well, you can see right here, that's going to go away. Why are we not having, why don't we have two Z's? Oh, yeah, because we're going to distribute this right here. Okay, so then we get this, all right, times, oh, it's going to go this way, here. Okay, we get that, times pi Z plus eta B. Okay, now what we're going to do is we're going to distribute that pi Z expectation pi Z prime Z pi. Okay, we're going to get that. So this here and this become this, and we're going to take this eta, and it's going to be distributed over here. Okay, so we had this PZ. Oh, and then we still had this PZ term here. All right, so then it's going to become plus expectation. Here's the eta prom, PZ, eta, inverse B. Okay, so then we have that term here. And then we're going to substitute the value of B in. Where was B again? Oh, yeah. Expectation, eta, prom, PZV. Okay. This here is this. All right. So when I take the bias of, or when I write out the, this is the writing out the bias. This I'm writing out the bias of two-stage least squares. It collapses to, it is approximately equal to this. Okay, so I've got all these expectations here. And let's see. If this right here could just be equal to 0, then there'd be no bias, but let's look at that because it would delete all of this, but let's look at what this would be. All right, so we've got here expectation eta prom PZ V. Okay, so it's expectation eta prom Z prom Z inverse Z prom V. All right, so we're gonna look at that real quick. This is the first stage error, and this is this error. So so we've got here this eta and V. So long as eta and V are correlated, okay, so long as eta and V are correlated, this does not go to 0. This does not go to 0 since they are correlated. And as a result of that, and you know that it's not, and you know that these two are correlated. You know that eta, the first stage, the X term, and the structural error, you know they're correlated, right? So why does Scott say, you know, V and eta are correlated? Because this entire exercise began trying to solve the problem created by V and eta being correlated. It was X was endogenous. X was endogenous in the causal model because X's eta term was correlated with V. All right. And so since these two are correlated, this expectation does not vanish. This expectation doesn't vanish. Now, in large samples, it will vanish because in the very large sample, this will go to 0 because Z and V are independent of each other. All right. But we don't have, it's this, we see neither this is represented with either of these. So this right here, pi Z prime V, okay, that's not there. And this, it's not there, okay? So this is what we knew was equal to 0 before, but that's not the same thing as this one. That's not the same thing as this one. So with some algebra, I skip a few steps here, but with some algebra, Angers and Pinsky showed that that bias term actually ends up being equal to this. And now notice this rule here. Okay, notice that. Let's go back. I'm gonna come back to this. Okay, look closely at that. Sigma Vn over sigma squared. Sigma Vn over sigma squared. All right, so that right there, this is the bias of OLS from earlier. And this, well, this is just the algebra and manipulation that I skipped, okay? Why is eta and V correlated? Holger asked, why are they correlated? You use two-stage least squares because X is endogenous, right? In the causal model. That's why you went for it. You said there was some unknown factor, eta, that is correlated with X and which is in our structural error term. So eta is in our structural error term, causing a correlation. All right, so eta is in our structural error term. And therefore we intentionally chose two-stage least squares. We chose two-stage least squares because we had a problem with X being endogenous. Right? We had a problem with X being endogenous. In these slides, X is endogenous means V and eta are correlated. They're not independent of each other. So the unobserved determinants of Y are correlated with it. So if unobserved determinants of Y are correlated with X, then which we represent with this eta term, okay? If it's correlated with X, then X is endogenous, and we went for two-stage least squares, okay? Now, what I've shown here is there is bias even with two-stage least squares. IV is biased. It is consistent, meaning large samples. But in finite samples, it is biased because that last term in that long expression does not go to zero except in the limit. Except in the limit. Here we have the bias. So everything we just did yeah, that's how I think of it. Shun, that's what I'm saying. The correlation between eta and V comes from the fact that eta is a part of X, which is assumed to be correlated with V. Assumed to be. Exactly. Assumed to be. That's probably something I'm not being very clear. We are assuming eta and V are correlated. We are saying I have a problem. X is endogenous. I'm going to use IV to solve it. Let me use two-stage least squares. When I decompose the two-stage least squares estimator and compare it with the true effect, I find that term containing V and eta showing up. But because of its complexity, it doesn't go to zero in its expectation. Doesn't go to zero in its expectation. It's being blocked by that PZ term. All right, being blocked by that PZ term. So when we go through, we rearrange it. We rearrange the expression. We rearrange the expression, and we get from here, so when we rearrange this expression, let me check one thing. Okay, so we rearrange this expression and it collapses to this one. So I skipped a bunch of steps to do that just because it takes a long time. But you get this expression right here. And so what I want to do now is I want to rewrite this. All right, so I'm going to rewrite the interior term into something easier to understand. Okay, we're going to rewrite it something easier to understand. And it turns out that this expression, this interior expression, is the population F statistic from the first stage regression on the excludability of the Z variable from the first stage itself. That's an F statistic. Okay, that's an F statistic. That's the expression of the F statistic. So we're going to rearrange that, substituting F for that big term. We can rearrange it one more time. Okay, and we get this expression. So the bias, again, right here, this is the bias, two-stage least squares. Okay, not zero. See these two terms. Okay, not zero. But what do we have? We have the bias of OLS. We have the bias of OLS. And then we've got this ratio. Ratio of 1 over F plus 1. F being the F statistic. Okay, so we've got this this expression here. Now look at what this is. Look at what this does for us. Even though the bias of two-stage least squares is not zero, notice if this right here, notice the larger F is, which measures the statistical strength of Z in the first stage, the larger F is, the larger the denominator is, the smaller the ratio becomes, the smaller the bias of two-stage least squares becomes. It never reaches zero, but with strong instruments, the bias is almost zero. All right, the bias is almost zero. The consistency property always holds. So when we have large samples, it always holds. But for small samples, it won't. So we end up here with 1 over F plus 1. So let's say that was, let's just use an example here. Let's say that F equaled 1. Okay, so that would be OLS bias times 1 over 2. Okay, 1 over 2. Let's say F equaled 100. OLS bias times 1 over 101. The second case has lower bias than the first. So we want instruments that are strong. That's what we want. We want instruments that are strong, because the stronger the instrument, i.e. F is larger, the bias of OLS shrinks, because that's the bias of OLS. But if you were to choose, let's say that you chose, imagine you chose a Z instrument, which was completely irrelevant for explaining X, right? Then the F would be 0. So you would have OLS bias times 1 over 0 plus 1 OLS bias. Now, what would that mean? Notice the bias of two-stage least squares here would equal the bias of OLS, right? Because you would end up having here the bias of two-stage least squares equals the bias of OLS if that right there was a zero. If that right there was a zero, then the whole thing goes away and you just have the bias of two-stage least squares equaling the bias of OLS. And that's what was meant. That's what was meant earlier when I said weak instruments cause the bias of two-stage least squares to be centered on the bias of OLS, right? Because weak instruments mean small f statistics, and small f statistics are in our shrinkage term, and f statistics are in our shrinkage term. So if the f is small, there is no shrinking of the OLS bias. So it's the same as OLS bias before, but if the F stage is very strong, then the two-stage least squares bias is approaching zero. Well, here's what's nice. Here's what's nice about this. You can test this with an F-test on the joint significance of Z in the first stage. That's what's nice. This F weakness problem is different from exclusion in that you can actually test with your data the correlation between Z and X. You can't test for exclusion, but you can test the issues with weak versus strong instruments using an F-test on the first stage, on the instrument in the first stage regression, right? But what this, so that's great. So here we finally have an assumption that we can test. Well, Melba says if F equals 0, it would have been, yeah, it would have been, if F equaled 0, then you would not have solved the problem, and your estimator probably, I think, is going to have more variance. So it's actually worse. You're going to be centered on the bias of OLS. Yeah, Angela. Yeah, so you're going to be centered on the bias of OLS, Melba, but probably your estimator is going to have more variance. So it's not really. So if you're trying to solve for the endogeneity of X using an instrument that is weak, you've not solved anything. You might as well just stick with OLS and just live with that bias. At least the variance term, the variance would be smaller. So you don't want to use weak instruments, which then leads directly into Angelica's question. Can we use this argument to support our choice of instrument if F is large? Yes, you can. So what you want to do, we'll get to that in a second, but yes, what you're wanting to do, you want to choose instruments that are strong. That's what you're wanting to do. The stronger the instrument, the larger the F statistic, the smaller the OLS bias becomes. And as the OLS bias falls, the bias of two-stage least squares is approaching 0, because that's all that the bias of two-stage least squares is. It's the bias of OLS. It's the bias of OLS in the limit. Two-stage least squares bias is completely the bias of OLS under the worst case scenario, which is an F of 0, and then it only improves. Okay, so you want to choose instruments that are strong. That's what you're wanting to do. If you have a choice between, so you want to be searching for instruments that are very strong. A couple of things, rules we've learned in instrument selection. Biggest, pick instruments that are plausibly satisfying exclusion. You can't do anything if the instrument is not excludable. Okay, so that's the very first thing that you've got to remember. You've got, and that is argued with logic and familiarity with the phenomenon. Okay, so you're having to argue for exclusion, and that's the hardest part. This is arguably the hardest part of selecting Z. Right, it's probably arguably the hardest part of selecting Z. But number two, having different Z instruments available, choose the Z with the highest F statistic. Okay, if you put all of them in and any of them are weak, then the bias of two-stage least squares gets larger. So you don't need all those instruments. You don't need all those instruments. You just need for the you just need one instrument per endogenous variables. All you want is for that instrument to be excludable and strong, high F statistics in the first stage. That's what you're looking for. So it's absolutely critical that you choose instruments that are strongly correlated with the endogenous regressor. Otherwise, the cure is worse than the disease. Worse than the disease. Why is it worse than the disease? Because the variance on the two-stage least squares estimator is larger than the variance of OLS. Yeah, this, Angelica, this is in my book. This is in my book. You don't have to buy the book, Angelica. It's available online. Remember that. It's right here. Right here. So it's in here. Okay, so you don't have to buy it. So adding more weak instruments, that's the problem here. Adding more weak instruments. Okay, if you add in instruments that are weak, it will increase the bias of two-stage least squares. All right, so don't do it. Okay, first stage F, by adding further instruments without predictive power, you're going to cause that F statistic. Every time you add in a weak instrument, you're going to cause that F statistic to go towards zero. Right? We're going to see this more closely when we cover judge fixed effects. If the model is just identified, weak instrument bias is less of a problem so long as the instrument is weak in the first place, is strong in the first place. Holger, the way that I think about the intuition, of the variance being larger is why is the variance of the two-stage least squares estimator larger than the OLS? When you estimate that first stage, recall that you're using predicted values of X. When you're estimating the second stage, when you estimate the second stage, you're using predictive values of X from the first stage, right? This X variable has less variation than the true X variable. Has less variation than the true X variable. Why? Because it's only the variation in X that is caused by variation in Z. So you've reduced the variation in X using two-stage least squares. The variation that you use in two-stage least square, the variation in X that you use is exogenous, so it can identify causal effects, but there's less variation. So as a result of that, the estimator isn't as powered. Okay, it isn't as powered, and so you can end up with this. This can cause the imprecision of the estimates in the second stage. Okay, it can cause imprecision in the estimates in the second stage. That's why you typically see OLS versus two-stage least squares having larger standard errors. Okay. They're not really comparable though. So if the model is just identified, so after Angerst and Kruger, there were all these papers highlighting issues related to weak instruments, finite sample bias. The issues with this bias of two-stage least squares are ultimately caused by the size of your data set, though. It's caused by the size of your data set, right? Why is it weak? Because in a finite sample, you can't detect statistically the strength of the correlation. In an infinite sample, you can. So this bias is ultimately associated with two-stage least squares because bias is a small sample or finite sample concept. Consistency is an infinite sample, large sample concept. All the bias of two-stage, there is no bias in the infinite sample because F equals infinity in the infinite sample, driving the bias down to 0, right? But in a finite sample, that's not the case. All right, that's not the case. So we have weak instruments, finite sample bias, and here were the papers, Nelson and Start. So remember Angerst and Kruger's 91. So you had a paper before it. You had a paper right after it. The authors appear to be, are these guys the same people? No, there's a bunch of B's, but they're not the same people. So you got Booz 1992, you got Becker 94, and you got Bound, Yeager, and Baker 95. And Bound, Yeager, and Baker was the only one that was focused explicitly on, this one was focused explicitly on Angerst and Kruger. These were, these right here, whoops, those were econometrics papers. All right, so these papers right here were econometric papers, but this one, Bound, Yeager, and Baker, it was about Angerst and Kruger. So let's look at what they do. So remember, they had 180 instruments. If any of them are weak, okay, so if any of the 180 instruments are weak, the F falls, the bias of two-stage least squares grows towards the bias of OLS, right? So we get that approximate bias gets worse. All right, so they're going to replicate the paper. So Bound, Yeager, and Baker 95 will attempt to replicate the original Angerst and Kruger 91 paper. But this is funny. Their Z variable will be a random variable generated with a random number generator. It'll be completely independent of X. No explanatory power at all. All right. So that's what they're going to do. So they're going to add in weak instruments for the first stage F statistic. Okay. So right here, when they do it, they are not able. So they can't perfectly replicate, but they get somewhat close. I think they didn't have Angerst and Kruger's original programs. They didn't have their original programs back then. Back then, no one had to share programs and data. So they did their best, and they get 0.063 for OLS. It's their IV that's much larger there. AK had a two-stage least squares estimate of around 0.09. They have 0.142. So their IV estimate is way different, but let's ignore that for now. Okay, so what we're gonna do is we're gonna put this in, and this is the quarter of birth. This is the quarter of birth instrument. All right, and it's very, very strong. Then they're gonna put in, so they're putting in quarter of birth. In a minute, they're gonna also put in a random variable to show the same thing. But when they put in more weak instruments, notice they do this. They got in 30. Notice what happened. The F statistic fell, and we're getting coefficient estimates that at least we can't observe this, but whatever this bias is, its bias is approaching over here. So we don't actually know what the bias is. So this could be like the true effect could be 0.08. We're just knowing that the bias of two-stage least squares is getting closer to it. Then they put in 180, and they do have this very precise estimate, but the bias, putting aside the standard errors, the bias of this right here is equal to the bias of this one as this F statistic goes down. So what do? This kind of gets back at least to how I was kind of interpreting Angelica's question. What exactly is the practical guidance? So this is the practical guidance. The practical guidance. Number one, use a just identify model with your strongest instrument. Because we have less worries about weak instrument problems in the just identified case, using a just identified model has good arguments. So use one instrument per endogenous variable where that instrument has a large F statistic in the first stage regression. Okay, so that's the first thing. Use a just identified model with your strongest. There are alternatives, though. There are alternatives to two-stage least squares. Keep this in mind. Everything we just did, which estimator was it? It was two-stage least squares. We just showed that the bias of two-stage least squares was centered on the bias of OLS. We didn't show it for other IV estimators. Some IV estimators do not suffer from the same finite sample bias problems to the same degree as two-stage least squares. And there is one alternative you can use based on maximum likelihood called limited information maximum likelihood, or LIML. Okay, it is approximately, here it is, approximately median unbiased, but you need constant effects. It's got the same asymptotic distribution as two-stage least squares under constant effects, but you get this small finite sample bias reduction. Let me just say one thing. In my experience, I have never seen LIML improve over two-stage least squares very much. Okay, I've never seen it improve over two-stage least squares very much. So if you have a weak instrument problem, I wouldn't put much confidence in solving it with LIML. It's probably the case you need to abandon that instrument, unfortunately. Okay, so if you have weak instruments, it's really this one. If you have a weak instrument, the real solution is to not use it. You need to go back and find a better instrument that is still excludable, right? So let's get into some practical IV tips. So really the two things that I wanted to show you. So far under constant treatment effects, we've really emphasized just a few things. Exclusion is critically important. Okay. You must have excludable instruments. Okay. Excludable instruments. And this is okay, so let's just draw this real quick. Here's what an excludable instrument looks like. Here's what an excludable instrument looks like. Notice this is a picture. This is a picture of an excludable instrument that I want you to always remember. Okay, notice Z is independent of U, of confounder U. Z does not cause Y directly, right? Exclusion is the strangeness property I mentioned, okay? So you need an instrument that really is strange with respect to Y. It is something that does not belong when trying to explain Y. The less intuitive the Z instrument is when trying to explain Y, the better, the more excludable it is. So you use logic and familiarity with the phenomenon you're studying. Okay, this is the hardest part of IV for people. They tend to not think hard enough about excludability. Oftentimes when I teach IV to students, to undergrads and masters, they will choose an instrument based on strength alone. This is wrong. Okay, so you cannot, and the reason they do that, the reason students do that is because they are inexperienced. They often are studying something for the first time. So they don't have much familiarity with the thing they're studying. So they have trouble articulating an instrument that is excludable. Okay. But it doesn't matter, it doesn't matter. You have to discipline yourself now to only be open to excludable instruments. And since you don't have statistical tests for it like you do for weakness, you have to spend you have to convince yourself of that diagram using logic, history, conversations, discussions with experts, familiarity with the thing you're studying, and do your best, right? Do your best. It needs to be a good faith effort at satisfying that diagram. Okay, it's got to be a good faith effort at satisfying that diagram. So now, having said that, and then the second thing we've looked at is strength. Now, having said that, what are some practical IV tips? Number one. Oh yeah, let me look. I got a thing here. That's a good point. Yes, Shun, that's excellent. There's a trade-off between efficiency and bias when adding more instruments. I believe that is right. I don't know. I don't exactly know how to articulate that trade-off. You can reduce standard errors with more of them, but then you're back in that world where the bias is exactly what you started with, and that precision may not improve over the precision you had with OLS. Does the instrument need to be at the same level of the endogenous variable? No, it doesn't, Melba. It does not have to be at the same level. No, it just needs to satisfy the exclusion criteria in the first stage. That's all that it needs. Before we do this, this discussion right here, this practical IV tips, would it be okay if we took a 10-minute break real quick? I'll be right back. I just want to take a real quick 10-minute break, and I'll be back at 22 minutes on the hour. I'll be back at 20 minutes on the hour, so an 8-minute break. I'll be right back. Okay, we'll get back to what we were doing. All right, so let's look at the reduce. Let's look at some tips. Okay, tips. That's a phrase in the United States. So let's look at some practical. This is some practical suggestions that I think you should follow in your research that uses instrumental variables. All right, that's all I'm saying here. The first is, I think people, readers, and audiences should be given the reduced form. The reduced form is ITT. It is often independently interesting to readers. Okay, it's often independently interesting to readers who are not comfortable with making a lot of exclusion assumptions. All right, just remember, reduced form does not identify the effect of the treatment. It identifies the effect of the instrument. Okay, it's just the instrument is only correlated with the outcome via the treatment, but keep that in mind. All right, so if you can't see the causal relationship in the reduced form, people are going to think it's not there. There's a certain art to instrumental variables. Why? Because the exclusion restriction is not testable. So you have to build the case slowly to convince the reader. Show them the reduced form. All right. Report the first stage. Always report the first stage. It is a sin when estimating effects with IV to only show the second stage results. Readers need to see the first stage because remember, first stage is the only part of this that is testable. So definitely focus on it. Show them that your instrument is highly correlated with the treatment variable. Okay, show them that it is. I think I left something out. Yeah, here we go. All right. So report the first stage. This is a personal preference of mine. This is a personal preference. Goal, make beautiful tables that are that people love to interpret. Okay. I personally think usually that means having the first stage estimates in the same table as the second stage, but that's just personal preference. You do whatever you need to make the table readable and beautiful. Okay, and it could be more than one tables, right? Goal is, though, report the first stage. So you want to report the first stage because you want them to be able to say, do I think that this, so be prepared. Here's the things you should be prepared for. Be prepared for these kinds of questions. Does the sign on the first stage on the instrument in the first stage regression make sense? Is it the correct sign? Is it the correct sign? Okay, so that's one thing. Two, those magnitudes on the coefficient in the first stage, should it be that large? Does that make sense? Okay, so be prepared to answer questions about the coefficients on your instrument. It should be logical, whatever it is. Okay, it should fit economic theory. Yes, you do, Angelica. You still you'll have to get an F statistic produced from software to get that estimated simultaneously. But yes, you'll still report the F statistic. The F statistic you'll report. The first stage, you might show those individual regressions with those instrument coefficients. But in terms of the F statistic, you're going to report the F statistic for their joint significance. Right here. So you need to report the F statistic. Now, yeah, you need for, I mean, you need for, let's go back to this picture. I'm only drawing this picture because I find it helpful for me to have this picture. Okay, so this right here is first stage, right? So all you need for Z to be independent of U. That's the confounder you're worried about. And you need for Z to be, let's just put it in like this, actually. Let's call it V. All right. So I got something like, I've got some structural error term here. Okay. So you need for, you need Z for Z to be independent of the structural error term. All right. So U was the confounder that causes X. That was at eta. All right. And then V was over here. You need Z to be independent of the confounder, and you need Z to be independent of the structural error term. Yeah, Melba, that language, you're right. You're right. I tend all that what they typically say is so all variables in the first stage regression are called instruments must be included in the second stage. All right. So recall they want, but the technically correct language is to say excluded instruments. All right. Z is the excluded instrument. That's the F statistic that we're focused on. All right. That Z won't be in the second stage regression. All the other covariates will be. So, yeah, thank you for bringing that up. I don't know. I don't personally like that language, but they are all being used for predicting the X term in that first stage. So they are technically all instruments. I just find it clumsy to always be saying excluded instruments. But yes, you're absolutely right. They're all instruments. They're just not all the excluded instruments. So how big does it need to be? How big does that need to be? So let's go back to that. Bias of two-stage least squares equals bias of OLS times 1 over F plus 1, right? So how big should F be in practice? There's not a good answer to this. There isn't a good answer to that question. There was a famous study, though, done in 2002 by Stock, Wright, and Yogo. It was filled with simulations. What they found was under homoscedasticity, F statistics greater than 10 had to appeared to be strong enough. So now economists are very focused on this F statistic of 10. This F statistic of 10. If you have more than one endogenous regressor, so this was what I was kind of holding off on a little bit. Angelica asked, what if you have more than one endogenous variable? If you have more than one endogenous regressor, right, for which you want to instrument, you don't report the first stage F statistic. You have to report something called the Cragg-Donald EV statistic. But the Cragg-Donald EV statistic is available in all of these IV packages. Okay, so you can report that pretty easily. Okay, so that's the thing you want to focus on. You want to present the F statistic, not just the you want to present the F statistic and not just the coefficients. And then lastly, you want to present OLS. In my opinion, this is just my opinion, but I think you want to present the reader with that original naive OLS model. Okay, you told the reader it was biased, so let's see it. So this is a lot of information. This is a lot of information. Reduced form, first stage, F statistic, OLS, right? One table. Well, you may not be able to get all of it in one table, but here's an example of at least 3 of them. This has 3 of the 4 things I said. Hold on one second. This has 3 of the 4 things I said. Angelica says you have 2 endogenous variables. Do you need to include? Yeah. So yeah, let me, I probably wasn't clear. So you have to have a just identified model. A just identified model requires having as many instruments, as many excludable instruments as you have endogenous variables. So if you have 2 endogenous variables, let's say experience and education in the schooling regression. If you have 2 endogenous variables, a just identified model will have 2 excludable instruments. Okay, so you're gonna have to report, you'll have to have both of those. All right, so here's a picture of a table as a possibility. So this is an example of an IV table you might consider copying in your research. And the reason is because it has several of the elements that I mentioned. Hold on one second. I'm working. I can't talk. Where's my clothes? There, all your clothes are in your drawers. Put them up? Yeah. Yeah. Okay. This is an example of an IV table that you might consider copying in your research. And the reason is because it has several of the elements that I mentioned. So for instance, column 1 is the bias OLS model. Column 2 has 2-stage least squares second stage results. B, first stage coefficient at the bottom. C, F statistic at the bottom. Okay, so it's just missing the reduced form, but you could have had a third column if you wanted. It just might, you just want to make it beautiful. And if it doesn't come naturally to you, you might want to get advice from a colleague to see if the table is confusing. Okay, but here I sort of see some of that. So I see right here, I've got my OLS model, right? My OLS model, education causes for every additional year of schooling, wages go up 7%. When I use 2-stage least squares, I find that for every additional year of schooling, wages go up 12%. All right. I used as my instrument whether the person lived in a county with a college. Okay. So again, think of the strangeness property. Why should growing up in a town where there was a college in your county be relevant for your future earnings? All right. Well, what if I told you you lived with your parents and attended the school? The school being close to where you lived meant you didn't have to pay for a dormitory. Okay. Then we see at least some of the strangeness logic here. Okay. So I got the college in the county, and then I've got the F statistic here. And then I just put in some other stuff. I put in some other stuff. Okay. So that's an example. I like this. If you go to the CI workshop and you go to STOUT, okay, there is code. All right. Let's see. So it's SSC install stout. All right, and then I'll show you. This is some code you can use. Okay, this is some code. So this file will estimate the returns to college education using college in the county. You'll use this right here. Now this is just how to make a LaTeX table automatically in Stata. So I'm going to run the whole thing. Let's see if it runs. All right, so I made some. I went through here. Okay, I went through here, and here's my OLS regression. I saved my estimates. Here's my first stage. Save my estimates. Let's see, where did I do my F statistic? Test. Here it is. Test the instrument. Here's the instrument. I do test right there. And I save the F statistic. And then I use IV regress. Right? IV regress, two-stage least squares, the outcome. I instrument for education with college in the county. I control for my covariates. I report the first stage information. It's going to save a bunch of statistics. It's going to save the mean and the variance of the outcome. I save all this stuff. I save my beta term, my standard error. So that's the beta on this, and standard error on that. And I pull out a bunch of other stuff. I get the Anderson-Rubin test for weak instruments, and then it just creates it all in LaTeX because I use everything in LaTeX. Well, let's go over to LaTeX now. All right, I'm going to open this up. I go to CI workshop, go to stout, and I believe I'm going to this one. Let's see. Yeah, that's what I'm doing. Going to this one there. All right, so I ran this. Okay, ran that. It produced this table. Well, let's run it. And it made this beautiful table for me, right? I never had to actually manipulate anything. So I have example code of how to make a beautiful table in Stata. I don't have it in R, but I do have it in Stata. Okay, so you do have some options for trying to create the tables, yourself. But I just sort of present this right here as sort of an example. Okay. If you have many instruments, in my opinion, pick your best one. Report the just identified model. Check your over-identified two-stage least squares models with Lemel. And then lastly, make beautiful pictures. Okay. Show pictures of the first stage. Show a picture. You can't really show a second stage picture. Somebody asked yesterday, I think it was Melba or Angelica, have I ever seen a second stage picture? I have not. Just because it's usually a multi-dimensional, regression, so it's a little bit harder to do. But you can show pictures of the reduced form. You just got to find a good way to do it. So this is from a paper of mine where we're looking at the effect of an intervention in the United States on a particular drug called D-methamphetamine, and this is the price of D-methamphetamine. And this intervention caused meth prices to rise. Had no effect on cocaine and heroin. So this is me visualizing my instrument. This is me visualizing my first stage. All right. So I got here the periods of time when price quadruples or doubles, right? It's got these two supply side interventions. And here is let's look at the self-admitted methamphetamine. This is heroin and this is cocaine. So you got this. But then when prices rise, falls. When that ends, starts to rise back up again. When the price rises, falls. Right? So you see here, notice how much more compelling this picture is than if I just showed you a table of numbers and asterisks, right? The picture tells the story. The story goes, when the government, disrupted supply and caused meth prices to rise, it caused meth admissions into treatment hospitals to fall. I can see that in the time series. So I reported the time series. Okay, I reported the time series, even though I'm going to be using a panel data set. So you have to make some design choices. You have to make some design choices. You want to communicate what is driving your first stage regression best you can. All right, that's what you're trying to do. All right, so what I did was I had a couple of things in this that I'm trying to show them, which is that notice, meth was rising, then it falls, meth was rising, then it kind of flattens. You see it more sparkly here in the self-admits. Okay, it's much weaker here, right? You see nothing for heroin. You see a little something for cocaine. It's not really clear what's going on with cocaine. It had been rising. And then when meth prices rose, meth prices fell. Cocaine actually appears to be somewhat substitutable. So it's, right here. And then notice when prices, rose for meth, well, look what we get. We get this rise, then it goes back down again. So there's lots of information in this picture. And I promise your readers will enjoy pictures like this. Okay, it makes the reader feel empowered and helps them understand your paper, which is what you need. You need them understood and you need them engaged. Okay, so use beautiful pictures that tell the truth to communicate first stage and the reduced form. All right, so that's the first stage. Let's look at the reduced form. Well, for the reduced form, I'm going to do the same thing. Right, so this was a project. This project was about the effect of parental methamphetamine abuse on child abuse using foster care data. Foster care in the USA is when the government removes a child from the home because of abuse. Removes a child from the home because of abuse. Right. So I notice what I get here. Right. Fall. Rises. Falls. Rises. Notice. You can see the reduced form in this picture. You can see the decline in foster care during the period of time when meth prices were spiking, right? This is probably one of the reasons referees liked the paper, because they believed my two-stage least squares results based on this picture. You'd be surprised. You'd be surprised how important pictures are to the very best economists in the entire world. Right? They spend a long time trying to design the perfect picture. And so should we. So should we. Okay. All right. So that was everything to do with constant treatment effects. It was, kind of giving some practical guidance. And then we learned about two-stage least squares. It's just a barely touching on a lot of IV estimation, but we did that. Okay. So we went through two-stage least squares. We discussed weak instruments. We discussed exclusion. We had these practical tips. Now what I want to talk about is heterogeneity, right? Okay, so everything we did, we had assumed constant treatment effects, right? Constant treatment effects basically means that all we need for identifying causal effects, AT, is exclusion and 2 non-zero first stage. Heterogeneous treatment effects, where each unit may have a different response to the treatment. Heterogeneous treatment effects, where each unit may have a different response to the treatment, has more than just these 2 assumptions. That's what we learned in the mid-90s once Heterogeneity began working on this problem of IV, right? Heterogeneity. See what we learned from Heterogeneity, right? Right. So first thing that Heto does, this is from 2 papers co-authored by Embens. There's Embens and Angrist, 1994, and then there's Angrist, Embens, and Rubin, 1995. Okay, so there's 2 papers that we're going to be kind of thinking about. All right, and what he ends up doing is these authors introduce 4, not 2, potential outcome notation. Okay, they have potential outcomes in Y, and they have potential treatments in D. Okay, so the instrument relates to D, so they introduce D1 and D0. D1 is my treatment status when the instrument equals 1. D0 is my treatment status had the instrument equaled 0. Right? So, you know, voucher putting me in voucher to collect HIV results, voucher equaling 0 USD, right? That's the idea. So if I got an instrument of $0, then my treatment status is a potential treatment status of D0. But had I gotten any dollars, then my treatment status, I would have been given an instrument of 1, and my treatment status would be my treatment in a world where I got the instrument. Okay, so what we're going to do is, by introducing this new notation, we are going to analyze what IV is identifying. All right, what exactly is the interpretation of IV with heterogeneous treatment effects? Okay. So we're going to move from potential treatment status to observed treatment status here. So depending on what your instrument is, you're going to figure out what your treatment assignment is. So you're either going to get D0 or D1, depending on what this 1 is. So if this was a 0, you're going to be assigned D0. And if this is a 1, then this and this will cancel out, and you'll just be assigned your D1. Okay. And then we have here just a regression equation corresponding to this sort of switching, where this right here is referring to this pi term is the average in a regression. It's the average treatment status had you not been given an instrument of 1. And if you were given an instrument of 1, pi 1 is the causal effect right here. You know, pi 1 is the causal effect of the instrument on treatment status. All right. You can see it because look, that right there is causal effect. Okay, it's the causal effect. It's the, when you're given a 1, your treatment status is going to change from D0 to D1. It may or may not. Okay. Now, here are the assumptions you need for identification under heterogeneous treatment effects. You're going to need that stable unit treatment value assumption. You're going to need random assignment. Right? So this just means independence of the instrument. You're going to need exclusion, same as before, non-zero first stage. And this one, this is the newest one. Okay, this is the newest one. So Sattva, what does it mean? Let's just go straight to examples. Okay. Angrist has a paper estimating the effect of winning the lottery in the Vietnam War on serving in the military, and then using that IV strategy to estimate the causal effect of serving in the military on lifetime earnings. All right, on lifetime earnings. So he's going to use as his instrument whether you won the lottery. Right, higher values of Z going to cause some people to serve in the military. All right, so let's see what Sattva means. Sattva means if I'm drafted, it can't affect whether or not someone else is drafted. Right, so Sattva means if I am drafted, meaning my Z value, then your odds of being drafted haven't changed. Don't change. Okay. So that's all that Sattva means. This is no spillover from the instrument. No spillover from the instrument. I can't change your odds of serving in the military just because I got a high draft number. Now that could happen. It could happen in some other situation, right? But I'm just giving an example here where in the United States, it wouldn't have mattered. All right, it wouldn't have mattered. Independence assumption, let's just go back here. Look exactly what it means. This is all the notation for it, but here's what it means. If my draft number was generated by a random number generator, then it satisfies independence. Okay, so usually there are 2 ways to test for independence. Ask someone who works at the office that gave you the instrument. All right. So if it's that, if it involves that kind of administrative data, right? Ask them, how was this variable generated? Ask them until you learn it was generated via an Excel command or something like that. Okay. Number 2, balance test. If it's random, then covariates should have the same means across the values of the instrument, right? Well, that's testable. You can do balance tests on the instrument to see if it's truly random. Truly random instruments should have same means of covariates for all values of the instrument. For a binary instrument, that's pretty straightforward. For a continuous one, for a binary instrument, it's straightforward. For a continuous instrument, you will need to explore alternative ways to do balance. I can show you how it's done in the Judge fixed effects literature. Okay. But it's all about the randomness of the instrument. It's all about the randomness of the instrument, in other words. It's not about exclusion. So this right here, independence, the randomness of the instrument is not the same. It's not the same thing as excludability. Not the same thing as excludability of the instrument. They might seem like they're identical or implied by each other, but they are technically different, as I'll show. Okay, they're technically different, as I'll show. Right. So we need in this heterogeneous treatment effects world, we need independence. Sometimes it's called exogenous. Exclusion. All right. What does exclusion mean? Let's go down here and look at this example. If your draft number is correlated with earnings only via the instrument's effect on enrollment in the military, then exclusion holds. If the draft number, though, which was random, caused you to go get more schooling, exclusion is violated. All right. So think about it for a second. Think about it for a second. I win a high lottery number, which makes me go to the Vietnam War. But the US gave exemptions. For instance, grad students didn't have to serve. So maybe when I win the random lottery, instead of going to the war, I go to graduate school to become an economist. Then I don't have to serve. Well, graduate education causes my earnings to change. So now my instrument is directly causing my earnings to change. And if the instrument has a direct effect or a mediated effect in any way other than through its effect on military service, then exclusion is violated, even though the instrument was random. Okay, so we need military service this okay, so we need lotteries. Actually, I'll do the lottery. I'll show the lottery too. Let's just say it's a, got some random variable here and it's causing the lottery, right? So that's, here we have independence. Independence only concerns itself with the lottery, not the effect of the lottery. All right. This is exclusion. Exclusion describes this entire diagram, not whereas independence describes just the instrument and not the instrument's effect on outcomes or confounders. Okay, so you need both with heterogeneous treatment effects. Okay, you need the lottery to be as good as random, and you need people to only respond to the lottery by going to or not going to military. That's exclusion. Okay. Now, when you go and present, I just want to tell you real quick, if you've never been in a seminar presenting an instrumental variables paper or having someone present an instrumental variables paper, you are missing something. And that is that people will really focus in a seminar, in seminars and reading papers, since you can't prove exclusion. Economists tend to become obsessed with telling stories that violate exclusion. They just, doesn't matter how ridiculous the story sounds to you in a seminar, they are going to do it anyway. Okay, so you have to be prepared. You have to be prepared ahead of time for a high level of aggressive skepticism about exclusion. Okay, it's almost going to be like a sport. All right, so you know, I did it here by telling this story. Okay, so just be prepared. Be prepared. Go into your seminars, go into your papers, anticipating that people are going to argue with you about exclusion. Do not be surprised that that happens. Okay, so typically what I do is very early on, I just try to defend exclusion first. My favorite papers that are using IV design. Well, right now, Nora, I've been favorite papers. They're usually natural experiments. Okay, so my favorite papers, you know, what are the characteristics of my favorite papers? One, strange instruments. Two, natural experiment based. So usually it's some sort of event or events that happened, rather than some weird statistically constructed variable. You know, so that's usually the kinds of things I like. Three, I really like I'm intrigued. Let's say that I'm intrigued by these IV papers called leniency designs or judge fixed effects. All right, I'm going to talk about those in just a minute. You talking about the Bardic paper, Oscar? You talking about? I like it. I discuss it in the book. I'm not a huge fan of Bardic instruments, but, well, that's not exactly fair. I've never used a Bardic instrument before, but the only reason I haven't is because the only reason I haven't used a Bardic instrument is because I don't work in trade, and I don't work in immigration, and I don't work in, I do work in labor, but I'm not really estimating demand elasticities. So some of the kinds of things that make Bardic a candidate, I never use it. I never use it. But Borisak's paper is an econometric paper, and it decomposes the Bardic instrument into what it is. I really like Isaac Sorkin and Paul Goldsmith-Pinkham's kind of companion Bardic paper. That one I find a little bit easier to wrap my head around, and there's some diagnostic tests that they developed that I thought was really interesting. So, I mean, some of these Bardic IV econometrics papers I like a lot. Is that the one you're talking about though, Oscar? Or are you talking about that Bardic paper that's in Review of Economic Studies from a couple of years ago? Because, you know, Borisak and Peter Hull, I think that's the one you're talking about, right? Yeah, it's Peter Hull, who's a co-author on that paper. Yeah, Peter Hull is a co-author on that paper. He's written more about IV. Peter is extremely interested in IV and continues to do econometric theory around IV. So, but yeah, I like it. I mean, I think we learned a lot from all those papers. We need the strong first stage. We have to check whether a high draft number makes you more likely to get drafted. We talked about that already. And then we have this really hard one. This is the new assumption, monotonicity. So what is monotonicity? Monotonicity basically means, sure thing. Monotonicity just means that the instrument operates in the same direction weekly for all people. So that means if the instrument shifts people into treatment for higher values of the instrument, it must either not do it. It must either have no effect on some people or positive effects on the other, but it can't have a positive and negative effect at the same time. Hold on one second. Hold on one second. Why?
Because there's a discount going on.
It'll have to wait. I'm working right now. We can't do it right now.
I can do it.
No, I have to go through and figure out.
I can figure it out.
Yeah, but I have to evaluate whether I'm doing it right now, and I can't right now.
Okay, I'm just saying it's discount. It's $50 off.
There'll be time.
Okay.
Right.
What time will you be free?
I'm done at 10 a.m. Okay, so monotonicity requires that the instrument operate in the same direction for all individuals. All right, so it's a little bit easier to understand. So what that means is you have, let's say you have two types of people. Okay, one person high draft, another person low draft. Okay, monotonicity is satisfied. When you get a high draft number, you go to war. When you get a low draft, you don't. Okay, that's monotonicity being satisfied. Monotonicity not satisfied. Two types of people. One, high draft. Person one gets high number and goes to military. Two, person two gets high number and doesn't go to military, or evades and doesn't go to military. Okay, so let me do it in my, let me actually need the whiteboard. Okay, so let's build this out a little bit more. Okay, monotonicity not satisfied. Let's look at John. John gets a high number and let's see, monotonicity satisfied. Right? John gets a high number and serves in the military. Or John had gotten a low number and didn't serve in the military. We call John a complier. He obeys his instrument's orders. Okay. Monotonicity fails. Bill and John. John is the complier, but assume Bill acts this way. Bill gets a high number and he runs away and hides. Or Bill could have gotten a low number instead. But when he got a low number, he strangely decided to serve. Notice how the instrument has different effects on different people. John obeys, Bill defies. Bill always responds in the opposite direction as John, right? So notice the instrument isn't weakly positive or weakly negative. You need no Bills or no Johns. You can't have both in the data. Monotonicity assumes weak positivity or weak negativity in the instrument's effect, but not these contradictions. They are assumed to not exist. In many applications, like this draft example, it's very hard to imagine monotonicity failing. Okay, because in this example, a person like Bill seems irrational. He dodges the draft if he gets drafted, but if he isn't drafted, he volunteers to serve in the military, right? So this is strange. This is strange. So we need monotonicity requires that the IV weakly operate in the same direction on all individual units. Either people ignore it or they obey it, but you can't have some people obeying it and some people defying it, right? So with all 5 assumptions, then you've got this walled estimator, right? You got that ratio again, effective Z on Y, effective Z on D. Okay, we write down in the numerator the expression of that reduced form, Y on Z. So we're going to use here potential outcomes for different values of Z. All right, so when Z takes on a value of 1 or 0, right, here's the Z term right here. Here's that potential status. Okay, so what we've got is when the instrument takes on a value of 1, for those individuals whose potential treatment status changes, we're going to get changes in behavior. So the numerator is showing that only the compliers are part of the numerator. Okay, compliers are people whose treatment status changes with the instrument, but some people ignore the instrument entirely. imagine imagine in your family, your father, your grandfather, and your great-grandfather were all in the military. And you're going to be in the military. 2, you serve in the military. If you get drafted, you serve in the military. If you don't get drafted, right? That does not violate monotonicity. Monotonicity was about weakly positive. It allows for zeros, just not those negatives and positives. Okay. Right. So right here, when we've got this, if y d11 minus y d00 equals 0, that's the kind of person who always serves in the military. If y d11 minus y d00 is not equal, doesn't equal 0, then that is the kind of person who complies to the instrument and only serves in the military because they were drafted. Otherwise, they would not have. The numerator is subsetting the data implicitly by focusing only on compliers. That interior term, if it's different from the other, if treatment status changes because of the instrument, then those outcomes are the only outcomes we are calculating. Okay? You see it again in the denominator, right? Anybody for whom their treatment status didn't change, anyone whose treatment status didn't change with their instrument, the denominator would be 0. Okay, so compliers, therefore, are the only ones contributing to the denominator. So what Embens and others showed us is that IV is only estimating causal effects for the compliers. Why is that relevant? We are estimating average treatment effects for just one group of people, not all the people in your data set. And with heterogeneity, heterogeneous treatment effects, if the complier population has very different returns to the military service than everyone else, this local average treatment effect for the complier population may not be informative, may not be as broadly informative about everyone as we might hope. It could even be the sign differs. Could even be the sign differs. So the late parameter is the average causal effect of D on Y for those whose treatment status was changed by the instrument. Okay. IV estimates the average effect of military service on earnings for the subpopulation who enrolled in military service because of the draft, but who would not have served otherwise. It's the only people. So you don't know the effect on that multi-generational warrior, you know, those people that are basically the 4th generation of warriors in their families. You don't know the effect of military service on them using IV. Their treatment status here doesn't change When they get drafted, that's a 1. They serve in the military. When they don't get drafted, that's a 1. They serve in the military. 1 minus 1 is a 0. So those people, they're not contributing to this calculation right here. The people that refuse to serve in the military, people that are draft dodgers, that's what they call them in the United States, dodging the draft. That's a 0 if they're drafted. That's a 0 if they're not drafted. They also are not contributing. I think probably I'm a complier. I cannot imagine running away from military service. It's my family's never served in the wars. My grandfather did, but we're not lawbreakers. It would be really hard for me to justify something like that. So I'm probably a complier, a reluctant member of the military. So we've reviewed the properties of IV using a very simple dummy endogenous variable, no additional controls. The intuition of late will generalize to most cases where we have continuous endogenous variables and instruments and additional control variables. Here is the 4 parts of the population. The compliers, notice when the instrument is 1, the treatment status is 1. When the instrument is 0, treatment status is 0. Then there's a group called the always takers. When the instrument's a 1, they serve in the military. When the instrument's a 0, they serve in the military. So notice it's always a 1. There's the never taker. So that's that warrior, that's the warrior. The never takers, if they win the lottery, they don't serve in the military, they run away. If they don't win the lottery, they still don't serve in the military. So the subpopulation with D1 equaling D0 equaling 0, they never take the treatment, regardless of whether they win the lottery, right? That's a never taker. So you see this in RCTs, right? In a randomized control trial, there'll always be someone that refuses to take the treatment, even though they won the lottery. We even saw that in Rebecca Thornton's paper on Monday. There were some people that, even though they won money, still did not go get their results. They were never takers. No amount of money is going to make them go walk that distance. And then you have defiers. Defiers are people who, when they win the lottery, refuse to serve, but had they not won the lottery, they serve. Their treatment status is affected by the instrument in the wrong direction. And what that does is the main problem with defiers is the IV estimate no longer has a causal interpretation. Effects are getting canceled out through the weighted average. Okay, so under heterogeneous treatment effects, going back to the paper using Angerson and Evans, Nora asked, what are some of my favorite papers using IV designs? This Angerson and Evans paper is pretty cool. I mean, I'm not crazy about the question. I don't really care about estimating the returns to having larger families. I can imagine, though, that's really important for macro questions, because it could inform various kinds of policies, tax subsidies for kids and things like that. But Angerson and Evans basically show that, if you have a third child, then using IV, then you'll work less. But it's not really estimating the effect of the third child. First, Angerson and Evans estimate the causal effect of having a third child, not a second, and not a fourth, solely because your first 2 children were boys or girls, right? So this is a late for a very strange subpopulation. And if the effect of a third child for these people is very different than the effect of a third child for everyone else, this late may not be as informative as we hope. Now, I suspect in this example that the effects are probably similar. But sometimes there are applications. There are applications where that won't be the case. Okay. So let's look at a judge fixed effects, because we're sort of running low on time and I want to spend the next hour and a half on difference and differences. I think most people, are probably familiar with the RCT, so I'm going to skip the lottery design. I don't really have a lot to offer on RCTs. I'm not an experimentalist, so I would need somebody like my friend Rebecca to really give a robust treatment of RCTs. Instead, I want to talk about the judge fixed effects design. I actually think these are pretty interesting. So what is a judge fixed effects design? While you're looking at this, I'm just going to put this up here. Okay, so what I've got here is some treatment, and I've got some person, right? But the person can't just be assigned to treatment. What happens is you must first pass through, a wheel of decision makers. Okay, so you've got this wheel of decision makers, and this is like, person A. This is like person F. This is like person C. Okay, so it's like A, B, C, D, E, F, G. It's like all these different decision makers. And each decision maker has a different bias of strictness. Some decision makers are really strict. They rarely give the treatment. And some decision makers are very lenient. They usually give the treatment. Okay? They usually give the treatment. You're going to use this wheel as an instrument for the treatment, so long as the wheel is randomizing the decision makers. Okay, that's what you're going to do. You're going to use this right here as your instrument for this, right? And then what you're going to do is you're going to have some outcome. And you're going to estimate the effect of the outcome using that predicted treatment with that instrument. Okay. So it's very popular in criminal justice because in the United States, we randomly assign judges to criminal defendants. So we'll even randomly assign foster care caseworkers to cases. The reason why I like this, one of the reasons I like this, one of the reasons I like the leniency design or judge fixed effects is because administrators in government and firms actually do it all the time, but they don't hire economists all the time. So these leniency designs are out there and no one has used them because the people who own the data don't know the value of this setup they've created. So you just need to find them, find these people, become their friends, and get their data. That's what you got to do. And I like that. I like those instruments that reward hard work, right? Hard work and creativity. So let me tell you about a paper that uses it. So this is a picture of a judge fixed effects design. So you've got, you know, like a lottery, a wheel of fortune spinning around, and you don't know what kind of judge you're going to get. You might get the lenient judge, you might get the strict judge, you might get, you know, someone who is indifferent. All right. So I'll do this really fast. I'll tell you a little bit about this paper really fast. So there's this paper by Anna Azer and Joe Doyle. They were interested in the causal effect of juvenile imprisonment on future crime and schooling. All right. So they wanted to know, if I send a child to prison, are they going to commit more crimes in the future? Or are they going to commit fewer crimes in the future? All right. Are they going to finish high school, or are they not going to finish high school? So, extremely important question. The US has the world's highest incarceration rate in the whole world. All right, that's the problem with the United States, or you could think of it as a problem. I mean, we tend politically, there is a group of people, I probably am a part of that group, that feels we should be approaching our crime problem different than the way we are. And this paper is part of that reason for me. So we have it's a very important question. We incarcerate the most people in the world. We incarcerate 500 prisoners per 100,000, and we have over 2 million people imprisoned. We have almost 5 million people under supervision. The next highest incarcerating country in the world is South Africa for juvenile incarceration rates. Our juvenile incarceration rate is 5 times higher than South Africa. So South Africa is number 2, and we're 5 times higher. We have 70,792 children in prison in the United States in 2010. Okay. Now, if I'm wanting to know the effect of juvenile imprisonment on incarceration, the problem is you can't, if you want to know the causal effect of juvenile incarceration on adult crime, you can't just compare adults who had and had not been incarcerated as kids because of the selection bias problems. The people incarcerated as adults typically are very different people than those who hadn't. All right, than those who hadn't. Okay, so we need an instrument because juvenile incarceration is correlated with the unobserved criminogenic factors that determine a decision to engage in crime as an adult, right? So we need an instrument. We will use as our instrument, or rather Anna Azer and Joe Doyle, we will use as our instrument the randomized judge that you saw as a child. And I'll explain how to construct that instrument. All right, so here's going to be our instrument. We're going to use this right here. This Z is a measure of the tendency of a judge to recommend incarceration as a child using their average recommendation, average sentencing, in all their other cases, ignoring the one that this particular child was in, right? So let's think about the strangeness property. Why would Judge A's strictness with all his other defendants be relevant to how he decides on mine? My case is different. Their case had different lawyers, different evidence, different crimes. Surely they're impartial judges and can evaluate each case on a case-by-case basis. But if they tend to be somewhat biased in their decisions to punish, then even though it was random that I got Judge A, his other cases may matter to mine because those other cases capture his strictness. All right. Okay. So Anna and Joe Doyle are going to propose an instrument, and that instrument is going to be the propensity to convict by the judge that the youth was randomly assigned to. So it's going to actually be a propensity to convict by the judge. So let's think about it right here. Judge A, right? Bill, sentenced, guilt, incarcerated, 1. Ben, incarcerated, 1. Janet, not incarcerated, 0. Okay. Average incarceration is 2/3 of the time Judge A recommends incarceration. Now, Judge A is seeing me, Scott Cunningham. He has to decide whether to incarcerate me. I will use an instrument for his decision of 2/3, because 2/3 of the time in his other cases, he incarcerated the child. Right? Now, if the judge's decisions in these other cases really is irrelevant, then there will be no first stage. Think about that. If each judge is purely impartial and not influenced by bias, then there's no correlation between Bill, Ben, Janet, and how he decides in my case. Okay. So this is testable. In other words, this is testable, in other words, right? So if the judge assignment is random and the various assumptions hold, then the IV strategy is going to identify the local average treatment effect of juvenile incarceration on life outcomes for the compliers. All right. So the main idea is that you're using for your random assignment, you're using for your assignment to prison the fact that you got a strict or a lenient judge. Okay. And here was the data. They had 35,000 juvenile. So these projects, because of that finite sample bias, tend to be larger. All right. So they tend to be larger projects. So this is going to have 35,000 administrative records over 10 years who came before a juvenile court in Chicago, Illinois. Chicago is the capital of Illinois. I think it's a state. So, so we're going to have 35,000 juvenile administrative records who came before a judge, okay, for a juvenile court. Data from this 35,000 records is going to be linked to public school data for Chicago. It's also going to be linked to, that's going to be coming from the Chicago Public Schools. And then it's also going to be linked to adult incarceration data for Illinois. That's going to use Illinois data. So look at this. We have 3 data sets in this project. Juvenile records, juvenile court records, 2 high school student records, 3 adult crime records. We link them by name, date of birth, and physical address. Okay, that's how we're going to link them together. We're going to link them together that way. So these kinds of projects are becoming, you know, so one of the things I want to point out is trends in top economics journals for whatever. Take this for whatever it's worth. It's very common now for people to get these large administrative data sets and then link them together and relevant to get other relevant outcomes. They'll use personal identifying information that is common to all databases for this linkage. So you'll see incarceration's effect on earnings, for instance, because they linked incarceration records with earning and credit history. There's probably a lot of opportunities like this all throughout Africa, insofar as these questions have not yet become popular. These methods have not yet become popular in the continent population. So it's worth learning this, because at the moment, it's worth learning this because at the moment, this leniency design remains very popular and widely viewed as extremely credible for an IV design. It's still methodologically an active area in econometric theory, but it is still widely regarded very positively. All right, to answer kind of Nora's question about what are some good IV papers, these judge fixed effects papers tend to be like that. Okay, so I'm just kind of putting that in your head. If you think that you can build relationships with government officials and they digitize their data sets, and you could find if there's any kind of randomization of a decision maker, it doesn't have to be a judge, right? You just want to be thinking about this pipeline that a person moves through that gets assigned to a particular decision maker. That's really what you want to focus on. And if you can find that, then you might have a judge fixed effects or a leniency design type of study and it could be on a question that no one has ever been able to answer, at least in Africa, or at least in Kenya, or some other parts of the continent. You know, there could be really lots of great opportunities just laying around. I'm a big believer in saying this because at MIT or Harvard, people are often just wanting to work with those economists because of the Harvard MIT brand. But for the rest of us, we have to work really hard at getting to know people and building relationships, but they can really pay off. I can tell you at the end about a project of mine that took 2 years and I think is paying off. Okay. So what do they find? Here, I'm just going to, let me just give you kind of this is a sad paper. They found that if you incarcerate a child, they are 13 percentage points less likely to graduate from high school. Causal. Juvenile incarceration causes high school graduation to fall 13 percentage points. OLS, it's much larger, but that was just correlation. This is causal. It also increased adult incarceration by 23 percentage points versus 41. Okay, causal. Now, who are the compliers? Who are the compliers? Because this is only true for the complier subpopulation. This is the late parameter. So think about the complier. Think about the definition of a complier. D1, 1 minus D0, 0 is not equal to 0. Means that because I got a strict judge, I went to prison as a child. But had I gotten a lenient judge, I would not have gone to prison as a child. Okay. So this isn't identifying the effect on the always incarcerated or the never incarcerated. It's identifying the late for the only incarcerated because I got unlucky with the strict judge assignment. So this is the marginal child. This is the child who is incarcerated only because they were assigned to a strict judge. The strict judge and the lenient judge would actually disagree on the proper punishment of this child. So keep that in mind. This is a source of disagreement. Okay, the judge fixed effects. The judge fixed effects design is all about exploiting these kinds of implicit disagreements that hypothetically exist across the distribution of judges. All right. Okay, so I'm going to skip this part. I'm going to get into this. So here's the structural equation. Adult incarceration. Here's the outcomes. Y outcomes. High school graduation. Adult incarceration. Okay, so that's our Y's. Juvenile incarceration, JI. That's here. Court and defendant characteristics. Here. All right, so that's the model. And we are going to, in this paper, in this 2015 paper, they used two-stage least squares, which is very common. But today people will tend to use jackknife IV estimation also. They are numerically equivalent, but I will discuss that later. Okay, so we're going to look at their two-stage least squares and their instrument. Their two-stage least square model will be just identified. So there will be one instrument for JI. Okay, how will we construct it? Here's the construction of the instrument. All right, so here we have the average. Remember that keep in mind, remember my example where for Scott, the value of the instrument was 2/3. All right. For someone else, it might be 1/3, might be 1/2. For someone else, it might be 1/5. Okay. So these numbers differ per person because they are different judges, and B, they drop out different observations. Okay, because you're always dropping out your own observation. That's why it's n-1. So you're always excluding yourself. That n-1 probably is not a huge thing, but it could matter depending on it actually can matter for small number of judge cases, but for many times it's not going to be practically all that relevant. So we're going to get this leave one. It's going to be called a leave one out mean. All right. It's going to be called a leave one out mean. All right. So here's the average part. So what's this? This right here adds up all the decisions in the other cases, sums them, then divides by n-1. Okay. And that's how I got. So when I did it for Z Scott, it was 2/3. For Z Scott, it was 2/3. That would be ZJ here, based on all those other people. ZJ would be Scott based on Ben, etc. Okay. All right. So that was like, here it was like Ben, etc. equaled 2. 3 people total, 2/3. Right? Because there was 4 here because it was all of us, but I got to subtract me out of it. So it becomes a 3. 2, so it was 1 + 1 + 0. 1 + 1 + 0. 3 people total. Z, Scott, Ben, etc. equal 2/3 for me. All right. And then it's going to be for Ben, it'll be a different number. For Jill, it'll be a different number for that, even for that same judge. And then so even for the same judge, the number can be different, but then across judges, the number will be different. So there's lots of sources of variation that come for this instrument. You have 62 judges in the data. Average number of initial cases per judge is 607. There is substantial variation in the data. Now, this is what I'm going to show you right now is the typical way that you present this data, right? There's lots of pictures in a judge fixed effects paper, but they're fairly standardized now. So you really just copy them in your presentation, and the code is available on people's websites. So it's not hard to program, and the design decisions have largely already been made. All right. So what we're going to do is first thing we're going to do, first picture, show the variation in that Z variable. Now, if every judge always agreed, then given the defendants have been randomly assigned to the judges, it should mean every judge has the same propensity because they see the same kinds of defendants due to the randomization. All right, they see that. But if there are judges with different averages, it means something else other than the characteristics of the case is responsible for their decision, like biases or training or tendencies, something in the judge. Okay, something in the judge. So here's the picture. Here's the picture that you typically show. Now they've got a residualized and they got a raw. What's the difference here? So the raw would just be the 2/3 without adjusting for, you know, Ben being a female, Jill being Ben being a male, Jill being a female, some committing, a crime on a Monday, some on the weekend, etc. Right? So that's just the raw. Residualized partials out all those covariates and has a average tendency having controlled for observable characteristics, right? It's basically the same thing, just one controls for characteristics to net out those explanatory factors. And the raw doesn't. Turns out, even when you control for case characteristics, there is substantial disagreement between judges, even though judges have been randomly assigned cases. Randomized cases means on average, they see the same blocks, the same cases, same number of African Americans, same number of felonies, etc. Okay, so these differences cannot be due to the cases being different due to randomization. All right, so look what we get. All right, you've got the let's look at the residualized one. Right, you've got some judges that recommend that basically never incarcerate. You've got some judges that never incarcerate. Look here, you can barely see it right there. It's a 0. And you got some that incarcerate 22% of the time. So these are very strict judges. And these are very lenient judges. Right? And these are more like typical judges, the mode. Right? So really it's like, you know, you're kind of exploiting, you are going to be exploiting the variation in this tendency to recommend incarcerate prison by these, you know, more biased judges. Maybe bias is the right word. Yeah, tendencies. Okay. All right. Number 2. All right. I got a question. Hold on. Right here, Melba, here's the evidence for randomization. Thank you, Melba. That was a great question. All right. There's two sources of evidence for randomization. in this. Number one, you talk to the administrators. Talk to the administrators. In Houston, Texas, in the 1980s, they would use a bingo ball machine to assign defendants to judges. Bingo ball machine is basically a giant urn of balls, of ping pong balls, and you just reach inside of it and you pull out a number, and that number determined which court they went to. So, you know, just knowing institutional details will matter a lot for this. It's an easy way. It's an easy way to argue with your audience, right? But to Melba's point, maybe the bingo ball machine is just a story. Maybe it's not real. Maybe there's corruption. So, 2, balance tables. If it's random, then the characteristics of the judge's caseload should be identical across the distribution. Problem is, we don't have a binary instrument. It's a continuous instrument. So how do we do the balance test? We show means at different quantiles and then hypothesis tests on differences in means. We will report p-values and means for bottom, middle, and top tercile. It's up to you. But whatever you do, it should look basically like this table. It should look basically like this table. So I call this the balance table. All right. It's just using a continuous instrument. So this is our instrument, right? So here's our instrument, Z, the distribution going all the way down to the bottom, right? So this is going to be essentially bottom tercile, 0.094.147. So we're going to go 0.94. So it's going to be here, here, right? So we're going to be getting bottom. I think it's going to be something like this. I think it's going to be, I think this is the bottom tercile. I think this is the middle. And I think this is the top. All right, I think so. Or maybe this is the top. I'm not entirely, I don't remember off the top of my head exactly, but it's something like that. Okay, so we're going to be looking at means. And you can see, and we'll just look at a few of these, right? Pretty similar. 82.7% males, 83%, 83%. African-American, 72, 73, 74. Hispanic, pretty similar. White, pretty similar. Special education from high school, pretty similar. Where they're from, where they live, the census tract, where they grow up, poverty is pretty much the same, and their age, pretty much the same, and other race, pretty the same. All right, so you're going to report the means. And then you're going to do p-values on differences in means across these terciles. All right, so this one right here is the middle versus the bottom, right? So we're going to be testing for whether those are statistically different from one another. And then the top versus the bottom, that's going to be, that one's going to be top versus bottom. That's going to be this one and this one, right? So let's see what we get. You want p-values to be above 0.05. So that's not significant. That one's close. That one's close. Not significant. Not significant. So let's look at these right here a little more closely. All right. So this is just the middle to bottom. All right. So let's look at the middle to bottom. Okay, so let's look at that. All right, so these are different from each other at the 10% level, both of them at the 10% level. Well, how different are they? 72%, 73.7. So they're, notice, significance at the 10% level doesn't mean there is economic significance, right? These are precisely, these are still similar magnitudes, 72.4 versus 73.7%, or 18.9% versus 17.6%. Now, at some point, when you do enough tests, you will find statistical differences just due to false negatives. Okay, false negatives. Just at 95% confidence, you'll reject 5% of the time, right? By pure chance. So, you know, out of 20, we'll reject one. Out of 10, with 10% significance, we'll reject one, and out of 20, we'll reject two. So this is 1, 2, 3, 4, 5, 6, 7, 8, 16. So it's, you know, we rejected one by chance, nothing by 5%. So in my mind, you know, this is, I personally see this balance table and think, looks like randomization is holding pretty well. Each judge has, you know, on average, same kinds of clients with respect to observables, right? Randomization ensures unobservables too, but you can't test that, which is why I like to also be told by the administrator that they were randomizing. I like to see both, not just one. All right. So that's our balance table with a continuous instrument. Now we're going to present our first stage. All right. So the first judges leave one out, mean incarceration rate among first cases. Now, how do you interpret this? So the interpretation. All right. It's an OLS regression. So it's when Z goes from 0 to 1. Okay, Z goes from 0 to 1. We'll look back at the way that Z is constructed. So that would basically be going from 0 all the way to 1. So it's kind of a linear fit. It's a linear fit of this kind of, you know, incomplete. So it's extrapolating. There's a bit of some extrapolation that's being done with OLS. All right. That said, to go from being a strictly lenient to a very strict judge, you would incarcerate people at a rate. Now let's look at this one right here. Your incarceration will increase by basically 100%. It's OLS, so it, you know, it predicts beyond the support of the data, but it's basically like, you know, you get a lenient judge and a super strict judge, and your incarceration rate basically goes up uniformly. All right. High correlation. The thing I really want to emphasize here is notice very high correlation between the tendency of a judge and the decision in Scott's case, right? Even though Scott's case is different from Ben's, there's a correlation between how Judge A decided on Ben and how he will decide on Scott. Now, in real life, I only know my case, right? In real life, I only know my case. And of course, the judge is going to have reasons for his decision. But what all the data shows us is that his reasons can't explain all of his behaviors because he's different from other judges, even though everyone is randomly assigned cases. All right, so now we get our two-stage least squares results. Real quick though, did you notice something? Notice in that last table, where's the F statistic? Hazer and Doyle didn't report it. It makes me so mad that they did not report it, because you always report your F statistic. But look at the standard errors. Probably the F is very large. Usually in leniency judge fixed effects papers, the F statistic is the largest you've ever seen. The more discretion the decision maker has, the more bias he or she has, the larger that F statistic will be. Okay. All right, so let's look at the results. So here's the results. Result 1, high school completion. All right, let's look at that. So this is a bunch of OLS stuff for the Chicago Public Schools sample. Let's just go over here to two-stage least squares. All right, we'll just compare it. Let's compare it with this one. All right. Well, let's compare it with this one. Why don't we just compare it with that one? All right, so this is the same sample and using only the juvenile court sample. What do we get? OLS finds that if you finish high school, or sorry, if you go to prison, those people are 7.3 percentage points less likely to finish high school, not causal. OLS isn't causal because of the selection bias. Two-stage least squares is a causal estimate. It's causal late for the compliers. And it is larger, 12.5%. What does it mean? If incarcerated as a child, that child is 12.5 percentage points less likely to finish high school, caused by juvenile incarceration, not selection bias, if 5 assumptions of IV hold. Okay, that's the thing you want to keep in mind. We need all 5 assumptions of IV to hold. Results 2. Okay, adult crime. What happens to them? All right, so we'll go over here. Okay, so OLS finds that if you are incarcerated as a kid, those people tend to show up in prison as an adult 15.5% more likely than those who were not incarcerated, using the juvenile court sample. If you are using two-stage least squares, though, it's causal late for the complier subpopulation. Juvenile incarceration causes adult incarceration to rise 23.4 pp. If you incarcerate a child, that child, when he is grown, will be 23.4% more likely to commit an offense and go to prison for it as an adult. It would not have happened had he not been incarcerated, according to this analysis. Now we're going to look at heterogeneity analysis. Very typical for these studies to then look at, the effect of incarceration on pathways and other, pathways into prison or pathways explaining high school dropout, so that the reader has a better understanding of why this is happening. Okay. What he's going to do here, he's going to look at the type. They're going to look at the type of crime. All right. So look at the type of crime. Doesn't appear to be anything for homicides. All right. Because that's not significant. But that is significant. That is significant. And that is almost significant. That probably has a p-value less than 0.06. So they can't rule out zero effects. But it's close to significance. But these right here, they can rule out zero effects. So why did they go to prison as an adult? They committed a violent crime. They committed a property crime. Thankfully, they're not killing anybody, but they are committing violent and property crimes, other types of violent and property crimes. Now, why are they not finishing high school? Okay. They are not. Look at this. Are they ever present in the Chicago public school a year later? 21.5% less likely to show up. Now look at this. OLS, it's only 2, so it's actually 10 times larger than OLS. Here, transferred to another high school, OLS would give you a positive effect. Two-stage least squares says for the marginal student, they are 11.5. Oh, well, that's not even significant. Right, so there's not anything significant there. It's here. Why are they not finishing high school? They're not back in high schools. They've been transferred to adult correctional facilities. What about when they do go back to high school? So some do go back to high school. What happens to them? This is the advantage. They're taking advantage of their rich administrative data to tell a more complete story. Why are they not finishing high school? Okay. Well, they're not being placed in special ed, okay, special education, but they are being identified as having an emotional problem. They're 13.3 percentage points more likely to show emotional behavioral problems. They're actually shifting them out of learning disabilities and calling them emotionally disturbed. So it's a sad paper. It's a very important paper. Kind of suggests to me that from the perspective of trying to reduce the social costs associated with prison, the marginal kid shouldn't have been incarcerated. More generally, leniency designs are very powerful. They are very common if you know how to look for them. I highly encourage you to put in the back of your mind as you're just going about your research agendas. I encourage you to start thinking about questions that you might begin to take advantage of a design like this. And that doesn't mean that you drop everything and start doing it, but I encourage you to familiarize yourself with the design, because one day you're going to be having dinner or you're going to be having lunch with someone who works somewhere, and you just need to ask them some stuff. Obviously, you're not going to ask them about leniency designs. What I did in a project of mine was I took out a lawyer to lunch and bought them tacos and just asked them over and over and over again, explain to me how a person gets into this court. Why does this person go to this court instead of this other court? And finally, they told me that it was because of some kind of decision that was made at the jail, not the judge, but the jail. And that decision at the jail was due to randomized decision makers. Now, they didn't know that was relevant. Most of the time, the administrators don't even know to tell you about this randomized wheel because they aren't economists. They haven't been trained in causal inference. They aren't publishing for a living, right? So you have to find the right kind of questions to pull it out of them. And that's just the beginning, right? For a project of mine, studying mental illness in the jails, I did some research online and I found the name of a public defender, took her to lunch several times. Then she introduced me to someone else. Then they finally introduced me to the superintendent at the jail. Then I got introduced to the sheriff. That took about 6 to 8 months of just constantly going down, driving 2 hours to Austin, Texas, once a week, and just knocking on doors. And then finally, I got the data. And it start to finish has taken about 2 years, you know? But here's the thing. I'm the only one that has ever written the paper that I'm writing. I'm the only one that's even asked the question because no one ever had the data and no one ever had the research design. It could, Alexander. Alexander asks, would the randomize the wheel apply to teachers in a school? It very well could. You're going to have to satisfy Sattva. Keep that one in mind. Sattva is going to have to be satisfied. And so randomization within schools is oftentimes a little bit more challenging because the pupils interact with each other. But yes, you could look for that. You could look for that. You could look for any kind of randomizing device in the schools that is assigning a treatment. Let's just go back to what it is. It's the characteristics of this design. All right. Characteristics of this design. All right. So we've got treatment that you care about, right? Treatment that you care about. And you've got a person, right? Now, ordinarily, treatments are just assigned to people. Regression discontinuity designs, it's based on that running variable. But here, it's based on a wheel of decision makers, right? And you've got Judge A, Judge B, Judge C, Judge D, Judge Z5, 56, okay? You got all these judges. They each are assigning their own treatments. And this is a strict treatment. And this is a lenient one, right? That's a strict treatment and that's a lenient one. Now we still need, let's think through all the things that we need. Let's see if am I going to discuss this? Yeah. All right. So we still have all this. Okay. So what do you need to do? You need to figure out what's the treatment you care about. What are the outcomes? And can you link your admin data to the admin data with the outcomes? All right. What's the treatment you care about? Is there a wheel? Is the wheel randomized? How much discretion do the decision makers have? Do they follow a strict script? If they do, the first stage may be weak. If they don't, and they are biased, then the first stage may be strong, okay? But we still need to think carefully about the 5 obvious assumptions we discussed earlier. Still have to think carefully. about the 5 IV assumptions that we discussed earlier. All right, so let's look at those 5 IV assumptions in this context. So more often you'll see this before I go on, more often you'll see the jackknife IV. What it's going to do is you'll see Peter Hall has a note on his website, and in the note he says that the just identified model using the average propensity, e.g. 2/3, and two-stage least squared is actually numerically equivalent to estimating jive with judge fixed effects as the instrument, right? So if you have 60 judges, that's 60 instruments. Remember what we said about having lots of instruments. So Peter says the average propensity is in fact just a weighted average over those fixed effects. So the proper model is the jive. People do both. But the point is, if you have weak instruments, then you're going to need to evaluate that problem, just like we said before, right? Just like we said before, you're going to have to evaluate that problem, all right? Usually what I do is I present two-stage least squares with the just identified, because the just identified model uses as its instrument Z, that average propensity. And I can do balance tests using the continuous variable, and I can visually display the variation in the single variable. You could do things with the fixed effects too. It's just that visualizing balance for 60 judges, or estimating balance for 60 judges is a little harder, and visualizing variation is harder. So I do both, and so far it's been robust to both. Okay, just putting that out there though. All right, people will use both, but the main thing that we want to think about, are IV assumptions, sattva, exclusion, non-zero first stage, actually it should be independence, exclusion, 5, monotonicity. All right, so again, what are we doing? So we go, U, juvenile incarceration, outcome, Z, okay, we just keep writing this down. I encourage you, write this down every time. It helps you get your thoughts together, okay? So what you've got to ask yourself is, the whole diagram shows exclusion. The whole diagram is a picture of exclusion. So ask yourself, could Z and U be correlated? How? Could Z cause Y in some other way, some way other than JI? How? If the answer is yes to either, exclusion won't hold, right? So you have to think about this carefully, right? What does sattva mean? All right, so that one's for, that's for exclusion. right? Non-zero first stage. Oops, non-zero first stage. Right here. That's measurable with the F statistic. Okay, that's measurable with the F statistic. You know, balance tests. That'll help you know independence. So now we're just really down to sattva and monotonicity. Now, what does sattva mean? Sattva would be violated if when Scott was assigned the harsh Judge A, John was less or more likely to be incarcerated. Right? That's what sattva violations are. IV assignment to person 1 has an impact on treatment assignment of person 2. In this case, it's very hard to understand how that could realistically happen, right? Very hard to understand how that could realistically happen. But just because it seems easy to argue sattva here doesn't mean it always will be this easy, okay? You judge it on a case-by-case basis. But that's the reasoning of it, all right? That's the reasoning of it. So now we're down to monotonicity. Monotonicity. What does a monotonicity violation look like in a leniency design judge fixed facts? Let's say there are 2 judges, Judge A and Judge B. Judge A is harsh and Judge B is lenient, okay? This means anyone that Judge B ever incarcerates, Judge A would have incarcerated too, right? So there's never a situation where B incarcerates where A wouldn't have incarcerated also. Okay. But what if B is always lenient until it's a female defendant, and then B becomes extremely harsh, harsher even than A? Monotonicity violations in this design mean that this kind of change happens for the judges sometimes. Monotonicity means it never happens. Monotonicity means it never happens. Okay. Well, we can't easily test for it, but there are some new things people do to try and figure out how problematic it might be, right? And one of them is this paper by Franzen, Lefgren, and Leslie. Okay, Franzen, Lefgren, and Leslie. They propose a test. This is a test. This test is a test for the joint hypothesis that exclusion and monotonicity hold. Now, if you reject the null with this test, you just know one or both of those conditions are not met. You don't know which. Okay. But if you are 100% positive exclusion holds, which you may be, then it has to be monotonicity. Okay, then it has to be monotonicity. So it's a two-part test that generalizes something called the Sargan-Hansen over-identification test to assess whether treatment effects across judge propensities are possible. And I said this already. So that's one thing you can do. They show that the identifying assumption implies a conditional expectation of the outcome of interest. So this would be average. So the test would be basically look at the average high school completion rate, one of our outcomes, as a function of judge assignment and see if it's continuous. If there is evidence for a discontinuity in average high school completion rates across that judge propensity score, it means you rejected the null that assumed continuity of that function. And if you reject the null, you are rejecting monotonicity or exclusion, or both. So at that point, you have to argue whether you can rule out one of those. In my paper, I am extremely confident that exclusion holds. I won't want to get into it just to not bore you, but I feel very confident that it holds. In one of our 3 tests, we reject the null. And that means in our opinion, monotonicity holds, or monotonicity failed in that one application, that one outcome. Okay, means it failed in that one outcome, since we feel confident about exclusion. All right, so this test by Franzen, Lefgren, and Leslie is available on Emily Leslie's website. You just Google Emily Leslie economics, and you'll find it in her list of code. It's just that it's in Stata. So if you don't have Stata, you either program it in an R or email me and I'll do it. Okay, I'll write it for you. What people tend to do. So what if you reject? What if you reject? Are you done? Does that mean all that work was for nothing? No. There's another test, and it will allow you to estimate the late if you pass it. You just can't estimate, you just can't do some other analysis that people often like, called marginal treatment effects. What people will typically do is they'll check whether the characteristics, well, what they do is for this other test, they will break the data, they'll subset the data into African American only, or males only, or felonies only, or whatever. And they'll estimate first stage for just that sample. And if the sign on the instrument is always the same, they conclude that on average, judges are not changing their decision-making based on the characteristics of the inmate, of the defendants. And this is sometimes called average monotonicity. So if you fail Franzen et al., just do this subsetting first stage and see if it holds up. If it does, and it probably will, then you can proceed. Okay. My email is scunning@gmail.com. You can just Google my name, go to www.scunning.com, and you can find my email. So anytime, this is what I recommend. This is what I recommend, okay? When you are working on a IV paper, okay? Right? You write down this diagram, okay? Just highly encourage that you write down this diagram, all right? So let's mark this. U is unobserved, is not in the data, and is a confounder. D is the treatment. Y is the outcome. Z is the instrument, all right? Use the diagram to scrutinize your design, okay? So, number one, is Z independent? All right, so, what can we do? Is Z independent? Well, do balance tests. Ask around, right? This is how you evaluate the as if random assumption, okay? So you do balance tests, you'll ask around, you do those kinds of things, okay? So if you see someone presenting an IV paper, you're going to ask them about this randomness. You're going to ask them, you're not a jerk about it, but you're going to ask them, how confident are you that Z is random? How confident are you that it's exogenous? Is there any evidence that you can present for it? Maybe some balance tests. Tell me more about it, right? That's what you're going to be investigating. 2, non-zero first stage, right? That's the ZD part. You want to see coefficients, standard errors on Z in the first stage regression, and you want to see F statistics from the first stage test of the excludability of the excludable instrument from that regression. Okay, so that's here. So this is independence. This is first stage. But then 3, exclusion. The best way to assess exclusion is to do this. Okay, best thing you can do is tell a story where exclusion doesn't hold by drawing that arrow. What could question mark be? And how believable do you find that story? Right? So that's the 2 things you do. 2 things you do is put an arrow there, put a question mark. That means there's some ancestor to Z and U. Something causes U, something causes Z. That means to do this, you need a name for you. What is this confounder? Name it. Describe it. Okay, so that's the thing you want to do here. You want to have a name to this. You don't want to just be lazy and put something there. You won't know how to think about this IV problem if you don't have a description for the confounder. So you definitely want to be thinking about what exactly is creating the problem that's not letting me use OLS. Why do I even why do I need to use IV? Since I know IV has this bias in small samples, you don't just run to it, right? You don't just run to it for the sake of doing it because you're enamored with it. You got to have a reason for doing it. Okay. You got to have a reason for doing it. But having given this a name, now draw an arrow, some common cause. They both have some common cause. What could that be? Force yourself to tell a story. And then once you have a story about how Z actually is confounded, ask yourself, okay, given everything I know about this phenomenon, do I think that's a true story? Anybody can tell a confounder story. Do you think it's garbage? Or do you think it's believable? Yeah, Angelica. Angelica says there's just a tendency to be very concerned about the endogenous explanatory variable and how to solve it, but they don't do intensive work to look for the strong instrument. You're absolutely right. You're absolutely right. They're not doing it right. That's the thing, Angelica, that they're doing it, that they're approaching IV in a naive way, to be perfectly frank. They're being just as naive about instrumental variables as a lot of non-economists are about OLS. It's an old tradition in economics to be very lazy about some of these powerful estimators and think that the estimators sort of don't require being careful in thinking this through. But I will say this, Angelica, the journals will require it. Journal of Political Economy, Quarterly Journal of Economics. There is no reason that anybody on this call can't publish at the AER. There's no reason. I will go to the grave continuing to believe that any of us can do it. We just have to work harder than those guys at Harvard and MIT. Okay? We can do it. But if we do it, we have got to escalate. We've got to escalate our kind of the work that we do. All right. We've got to make it like this. We've got to present the strong arguments for the strong instruments. Strength in the first stage, strength of exclusion. Okay. So you're going to do this. You're going to tell a story where Z is confounded. You're going to decide how believable it is. And the reason you're going to do that, here's the reason you're doing that, is because someone in the audience is going to do that. That's the thing. You have to do this. You have to go through this exercise because someone else will, even if you don't. And they may be your referee or your editor. You have to anticipate what they will say and defeat it with the truth, right? Just this exercise can help you remember what you do and do not need to emphasize, right? This could have always been true, but you didn't say it in the paper because you didn't know that someone else was going to judge you harshly about it, right? So just do this hypothetical confounder thought experiment so that you leave your critic speechless, all right? You're trying to take away his toys, all right? And here's the second one you want to do. The second one you want to do. Is there any possible way that your instrument, even though it's random, could influence the outcome directly instead of just via D? Why? Tell that story, make it a good story, and then ask yourself, is there any evidence that that story could be true. Remember, economists become practically like storytellers when it comes to thinking about exclusion violations. They'll believe things in this part of the seminar that no sane person would ever in a million years believe, but they get away with it because it's just a sport, right? So be the first to state some of these and then explain if it's believable. Now, if it is believable, honesty dictates you take it seriously. Don't hear me saying to just practice getting into arguments with people, right? I'm saying anticipate bad arguments with evidence and logic. That's all I'm saying. If it's not true, have a reason for why it's not true, okay? Now, in the book, there is, I'll show you real quick. Go to the mixtape, go to instrumental variables. Oh, yeah, we're already there. Go to Jive. Down here, here we go. You got R code, you got Stata code, R code, Python code. And they will estimate, so we look at the R code, right? You can pull in this data from the internet. And you can, here's how you go through and do it. Let's see, where's the actual Jive? Is it Jive? Okay, here's all the fixed effects, I think. Or no, this was a pain to do this. Two-stage least squares. Here we go, Jive. So you can do two-stage least squares using, looks like it's this film command. Is that it? It's one of these. Actually, I'm not familiar with it, but here's how you do Jive. Jive.est. Use the Jive command to calculate this table right here. So I encourage you to also read this paper. I encourage you to read this. To read this section of the book. It's got some information that will help you. It tells the history of the design. Should give you plenty of information about, about this design, and give you the code. Most of all, give you the code to do it. Okay. And that's it. So for IV, oh man, for IV. To summarize, instrumental variables, extremely powerful design, very important. You're probably going to write some instrumental variables papers in your life. I would like you to consider at least kind of approaching it in the way that I've described, which is a deep attention to these identifying assumptions and the reasoning around it and the solutions around it. But I would also like to present to you the Judge Fixed Effects paper, the Judge Fixed Effects design. I continue to feel like, I guess one of the reasons I like the Judge Fixed Effects design too is it can help justify why you might start building relationships with agencies. And I do think for everybody on the call, if you could begin to think about the value of collecting administrative data, it opens up a world of research questions. Even if your IV project falls apart, you'll still have all this wonderful administrative data to evaluate this project, and you might get to go in a different direction. And oftentimes there is gold sitting in that. Now, obviously, you kind of have to have lots of projects going on to kind of figure out, to sort of balance out when some things don't seem to be going as well. But trying to get better about working with administrative sources, I think, is a good strategy to take overall. Okay. So tomorrow what we're going to do is we're going to do difference in differences. Could you recommend a journal for publishing the first paper? Well, I mean, ultimately, what you're wanting to do is you're wanting to publish a paper in the journal, the best journal that it has a chance in. Okay. So that means, trying to present it beforehand is a very good practice. I mean, I think one of the things that characterizes people who publish very, very well in very good journals, what's different about their papers? They actually presented it in seminars a lot. They presented it a fair amount. I have a paper at the Review of Economic Studies. It took a long time, and we probably presented the paper 10 to 15 times. The reason why you present it 10 to 15 times, to be perfectly honest, is you want to reach those referees beforehand. And you want to hear those referee criticisms beforehand. You want to try to get in rooms where you're with those likely referees and start getting their critical feedback now, fixing the problems now, so that when it does finally go to the journal, you've cleared it. Okay, that's part of the culture of economics publishing, is that seminar mechanism, that seminar world in the working paper world. So I highly encourage, no matter how uncomfortable you might be with public speaking, make yourself get on people's radar. Ask them, call somebody up and say, I'm going to be in town. Can you put me on a seminar? Get on Twitter, write threads, send them to me. If I can write it up on Substacks, I will. If it's in my wheelhouse to talk about that kind of thing, if you think it's a paper you think I'd like, more than happy to write about it on my Substack. So we can, you want to do that. And then at the end, ask around, where do you think I should send this? Ask people that are experts in the field, where do you think I should send this? Just because you get a rejection doesn't mean that you shouldn't continue to send it to good outlets. So where you should send that first paper really is endogenous to those things that I said. My first papers were not published very well. My first papers were my very first publication was in a medical journal on sexually transmitted infections, of all things. And then I published a book chapter. My first economics publication was at the American Law and Economics Review, which is not a very highly ranked journal. Then I slowly improved my publishing. So another thing, don't get discouraged by the fact that you're not feeling like you're publishing all that great. That's fine. There's returns to experience. Going back to, I believe what Angelica or Melba or someone said 2 days ago when they were talking about that Mensa regression. There's two things that determine wages. Education, that's done, right? You've already gotten your education. So that's done. You're getting education now in this workshop. Experience. That's the other one. Economics, empirical work in economics is as much, if not more, a function of experience as it is your education, your actual terminal education. So don't worry about it. Okay, you get a rejection. There's a novelist in America. His name was Larry Brown. He was a firefighter. He was a fireman, and he had something happen to him that made him want to start writing stories. And they were horrible. They were not readable. And he had 80 rejections before he got his first short story published. And he is now considered to be one of the greatest authors of the latter 20th century in the Southern United States tradition, which is this like rich literary tradition in the United States. It takes time. It just takes time to get your work going. Do not worry about it. Worry about the stuff that you can control. You can control the books that you read, the articles that you read, the projects you undertake, the data you collect, the estimators you choose, the conversations that you have. That's what you can control, though. What you cannot control is the publishing. All right. You continue to strive for the publishing, You try to do things that make it more likely, like I said, but at the end of the day, you can't control where the paper ends up going. So do your best to not care. Obviously, you want the better publications. I mean, that's the thing. You want your papers published in the best journals possible, if only because then other people will try to give you jobs and you'll get raises, right? I mean, even if that was the only reason, was that you might get a raise if you get better publications, then do it for that reason, right? Indirect utility is a function of income. You are happier. Even if you gave away all that money that you got from the raise, you will be happier, right? So absolutely strive for excellence in the work, write excellent economics articles, go through all, learn the rules, and publish. Do your job to publish as best you can by having a really wonderful scientific manuscript. But ultimately, in the day, you can't twist anybody's arms to make them like your paper. So you work on the stuff that you're passionate about. You work on the stuff that you love, right? All of the papers take the same amount of time, whether it's a good paper or a bad paper. It takes the same amount of time. So work on the stuff you love. Those are the easiest papers to write, the stuff that you're passionate about. Do not work on stuff you don't care about. It's very hard to get motivated to work on something you don't like. Okay. So it goes for IV too. So tomorrow we're going to do difference in differences. We'll do difference in differences. If we have time, we'll do synthetic control. But frankly, to be perfectly honest, everybody on the call, I think my best value to you tomorrow is to go into detail about difference in differences, because that is kind of the changing area right now. So we need to focus on that tomorrow. Okay. It's good to see everybody. I'll see you tomorrow. Y'all have a great day.